Hey everyone, this is Mrs. Shannon, and we are going to start talking about cellular energetics today. This is our first in our energy series. Again, we're going to follow the David Knuffke presentations, Prezis, and follow the PDQs that go with us. Now, the very first section here that we're going to look at, just cellular energetics in general, is going to sort of focus a lot on the thermodynamics. And if you took chemistry, a lot of it will look familiar with talking about activation energy and equilibrium. And if not, don't freak out because it's really not too difficult. Again, think about like biochem, the biochem unit. We're looking at patterns. We're looking at big ideas here. We don't need to get boggled down in all the little details. But for this one, I'm going to actually make a big screen. Oh, and don't forget, we are going through slides in class, but for the PDQs, just for extra practice, I am going to be still doing these videos so that you have access to them. It's just another way of looking at it. Okay, so the big questions in this Prezi are going to be, how do living systems adhere to the constraints of the universe? And how can a living system maintain order in a universe of increasing entropy? Okay, so we're going to talk about living systems here on the biosphere, planet Earth, when we know that there's a lot more going on out there. And so a lot of this is going to be centered around the idea of theory. Some of the ideas and some of the evidence that we have been able to gain to kind of answer this. So first of all, there's two relevant laws that you sort of need to understand, and they kind of form the basis of all of what we know in biology when it comes to energetics. And first is that matter and energy cannot be created or destroyed. Transformations are allowed. They can change form. They can transfer to a different location, but they cannot be created or destroyed. Okay. There's a few exceptions, examples, fusion, when we're looking at stellar fusion of stars. But we're not in Mr. Taylor's class. This isn't physics. We're going to focus on what's going on at the biological level. And for us, matter and energy cannot be created or destroyed. So here's an example of a bear. It's a living system. It's getting energy from the sun through the form of the fish and berries that he ate. The fish obviously ate something else that eventually, or at first ate some sort of plankton or phytoplankton to start its food chain. But the sun is the original source of energy. The energy made it into this bear. The bear processes it through the chemical bonds, and then work is able to be done. This process right here is cellular respiration. Work is anything that requires atoms to be moved around through cellular action. So anything basic. We're looking at the most basic chemical aspect of work. Two types of energy. Hopefully you remember this: kinetic and potential. Kinetic is movement. Potential is that possibility here. Okay, so if you have someone, just as a reminder of the two types of energy, if you have someone standing on a diving board getting ready to jump in, they have more potential energy, less actual movement at that time. Here, more movement going on, more kinetic energy, but less potential. When we're looking at energy, we're looking at the energy that is able to be used. And that's called free energy, a measurement of the amount of useful energy that a system like a cell can use for performing work. And we have a formula that is used to determine the amount of free energy available. At the cellular level, the major biological source of energy is from rearranging atoms to form higher energy compounds to lower energy. We're going from higher to lower energy. We're just rearranging to make compounds. And so we're looking at a lot of this energy derived from the breaking of chemical bonds. Okay, the breaking of chemical bonds. And so the formula of this free energy that's available is delta G equals delta H minus T delta S. And we've practiced that before. You're often, in order to solve an equation like this, you will be given values, and it's more of a plug or chug in order to solve it. Now we have what's called an exergonic reaction. In an exergonic reaction, it releases energy. Matter is converted from high energy arrangements to lower energy products. So the reactants had a lot more energy. Products have less energy in it. And so there was a release of energy in the process. This difference is the amount of energy released that's no longer going to be stored in a product. These will happen spontaneously once they are started. And you can recognize them when you're looking at free energy, when you're looking at Gibbs, because they are a negative value. Anytime you have a negative G, you will have an exergonic reaction, one that proceeds spontaneously. And this change between reactants and products is the amount of free energy that's actually released. On the flip side, you have an endergonic reaction. In this one, the products actually contain bonds with more energy stored in it than what they started with. They do not proceed spontaneously. They usually require some assistance, and we'll talk a little bit about that. They need energy added to it in order for the reaction to occur. So in this case, you can see the actual input of energy here for the products to be formed. This does not occur spontaneously, and this is less likely to happen in most biological systems. There are certain processes that will proceed endergonically, that they need that energy input. But oftentimes you'll see that most reactions are going to favor exergonic reactions. Biological systems use the exergonic reactions to provide the free energy that's necessary for the endergonic reactions we actually do have. So in order to power these that need an input of energy, we have to use this excess energy from the exergonic reactions. Okay. Living systems are not the only systems in the universe that require energy conversion to function. Here we have energy conversion going from like a hydroelectric dam here, converting the energy. We have the sun, solar radiation energy. But we're going to be focusing on biological systems. The second law that we're going to focus on is any closed system will tend toward a state of maximum entropy. It's true for the universe as a whole, but we have to remember that portions of the universe can still function as open systems. They're not closed off. We're looking at the universe as a whole increasing in entropy, but if we're just focusing on like the biological systems, it may not seem that way. And we talk a little bit about that in the notes. So life is highly ordered. Organisms use the energy they convert to power cellular processes that decrease their overall entropy, or at least delay its increase. This process increases the entropy of their surroundings. And so for this to be ordered, to remain highly ordered, or for this beautiful little Fibonacci sequence in the arrangement, in order to maintain this ordered structure, entropy is increasing around it. This disorder is increasing around it. It kind of keeps that balance, that yin and that yang. Life requires energy input. A highly ordered living system uses energy input to maintain this order. And we are fortunate enough that we have this constant source of energy input through the sun. So even though all this chaos is happening, all this energy is being expended, the sun is providing this input of energy. Okay, so closed system, isolated, hypothetical, dull, not true in nature. Okay, we can use them as models, but invariably they lack a lot of what you will find around you. Open systems, on the flip side, are more accurate in nature. Open systems will not reach equilibrium as long as the processes of the system receive inputs and produce outputs. So as long as something's turned on, it can still keep going. And this is the case with the example of the sun. We are constantly having this input of solar energy, and so we can constantly keep the system on. Life is an open system because we have this constant input of energy. Now, we're not destroying it. We're not creating it. It's part of the universe as it is. It's but we have enough of it that's being emitted from the sun that it provides our minute amount on Earth to sustain life to keep it going. Whoops, what was that last one? Once equilibrium is met on energy being received and output being received, once it stops flowing, that's when death occurs. Okay, ATP is the molecule that we're going to be focusing on as our primary storage molecule of energy. It's a short-term energy storage molecule, and it's small little molecule here, and we derive this through cellular respirations. There are tens of millions made and used per second per cell. Okay, it's the bonds between the phosphate groups here that are weak and unstable. Okay, they're very unstable. We have these negative charges here that are attracted to anything else that pretty much comes around it, and it's going to be pulling. The negative charges are also going to be repulsed from one another. Okay, they're going to try to get away from the neighboring electron or negative charge from the other phosphate, and so they're going to keep pushing away from each other. And so between being attracted to other positive molecules being repelled by neighboring electronic molecule, I don't know why I keep saying electric charged molecules, it creates a relatively unstable bond. Much more free energy is released when the bonds between them are broken than is required by the cell to initiate their cleavage. It's so easy to break it. Hardly any energy is actually needed to break it compared to the energy that's released once it's broken. Okay, exergonic reaction. Energy is released. Much of the work done by cellular proteins, when we're looking at crossing the cellular membrane, for example, during facilitated diffusion or during actually more so during active transport, much of the work done by cellular proteins is mediated by the addition and removal of phosphate groups from ATP. So we talked a little bit about active transport and pumps. They need ATP. They need that input of energy. We're going to talk about cell signaling and different ways that externally received signals can be processed and transduced internally. And a lot of that is powered by ATP and the energy provided. Now, when we look at metabolism refers to the sum total of all chemical reactions. And we're talking about catabolic and anabolic. Catabolic breaks down bonds, it breaks down molecules. Anabolic is used to form molecules, to build molecules. Now, oftentimes what we have is what's called a reaction coupling, where in order to get the energy that we need for a reaction to occur, like an endergonic reaction, we partner it with an exergonic reaction. If an endergonic process requires less free energy than an exergonic process produces, then coupling those two reactions will kind of allow for maximum efficiency. You still get that overall negative delta G, and so it's beneficial for it to happen. Now, all reactions require an input of energy. This is called the activation energy. It's sort of to get that reaction started, to get it up the hill, to turn it on. And this energy is needed to make the breaking of current chemical bonds favorable. So you have two reactants right here. You put in enough energy, okay, until eventually these bonds break. The relationship between the energy of the products and the energy of the reactants is what determines if it's exergonic or endergonic. So hopefully you can see in this case, lower products, delta G is going to be less than 0. It's an exergonic reaction. It is spontaneous. This is the transition state. That is another good term to recognize. Activation energy, you will want to know a transition state. Delta G, free energy, reactants, products, recognize all of those. Now, in order to lower this little speed bump, lower this input of energy that's needed to get it to go, we use a catalyst. And in a biological system, a catalyst is known as an enzyme. They are reusable. They don't participate actively in the reaction. They're just there to get it started, and then they release the reactant and go on to the next reactant or substrate. And so we'll be talking more about that catalyst, about that enzyme in the next David Knuffke Prezi that's up. And so we'll pick up there with that whole idea of activation energy as well. But from this one, you need to be able to make sure that you can explain how living systems adhere to the first and second laws of thermodynamics. And so for the first law, that transfer of energy, well, how is it transferred? What are some of the forms that it transfers between? How is an energy stored in an organism? How is it released in that organism? And so looking at the chemical bonds and like cellular respiration. You also want to be able, for the second law of thermodynamics, that's that increase in entropy. And you have to be able to realize that the energy is increasing in the universe, but we're only looking at a small part of the universe, the biological living systems. And so that can still, in order to maintain order, that energy is being used to maintain order there at the cost of disorder around it. Comparing inorganic and exergonic reactions. And when you compare these, that's comparing them in terms of what their delta G's are, if they're spontaneous or not, which one is and which one's not. How we can make the one that's not spontaneous more favorable for happening. The open and closed systems, know a little bit about that. More or less be able to recognize that living systems are open systems. We seldom use closed systems. We may start with modeling in biology at a closed system because it's easy to manipulate, but eventually we're going to work and see how something interacts at an open system. You usually see more closed systems in physics, which is a little bit more theoretical, or even maybe in a chemistry sense, where things are a little bit more abstract and theoretical. You want to explain how ATP allows for cellular work. And again, that's going to focus on that those phosphate bonds being very unstable, about how it takes less energy to actually break them than what's released. So it's very favorable to have them broken, for them to actually break, and it releases a large amount of energy. And explain the effect of a catalyst on a reaction profile. And so really focusing on how that catalyst affects the activation energy is what you'll want to know for that one. So I hope this helps. Go back to it. Between this and the Bozeman and the slides in class, all of your PDQs should be pretty much answered. If you do have questions still, just let us know.